Hello and welcome to mole molecule conversions. As we discussed already, a mole contains 6.022 times 10 to the 23 molecules. We'll typically actually drop this to for the sake of making our conversions a little bit easier. Sometimes we use it, sometimes we don't, but sometimes not having it there kind of keeps things simple from the standpoint of plugging in and worrying about significant figures. So there are two potential conversion factors here. You could say that there's 6.02 times 10 to the 23rd molecules, and actually that could be molecules or atoms, just means particles, in 1 mole. Or you could also say that 1 mole contains 6.02 times 10 to the 23rd molecules. So you can write either one on top, depending on what you need in your problem. Putting Avogadro's number into your calculator is kind of specific. Again, we are using scientific notation, so you have to find that weird little tiny E button. What I have up there is what it should actually say on your calculator. So you'll notice there's no times 10 to the, there actually is only one E. The calculator actually reads this button as times 10 to the caret. If you put a 10 in other than that, it will move your decimal place. And sometimes if you try to use the 10 instead, it will cause you other errors that I'm not quite able to explain to you. But, you just have to be cautious about this and make sure that you plug it in correctly. So if we want to know how many molecules are contained in 3 moles of water. So we're going to start by saying, okay, we got 3.0 moles of water, and we want to end up in molecules. I want moles to go away. So what I'm going to do is put moles on the bottom, and I can go right back to my other screen over here. My factor with moles on the bottom has 6.0 times 10 to the 23rd molecules on top. So I say, okay, 1 mole is equal to 6.02 times 10 to the 23rd molecules. Moles cancel out. And what you're actually punching into your calculator is going to be 3.0 if you're a stickler, times 6.02 E23. Now remember, this is going to read on your calculator with that weird little E. So I punched in essentially or I wrote up here essentially what it'll sort of look like. 1.806 E24 really means 1.8 times 10 to the 24 molecules. And I'm sticking with my sig figs there. 3.0 limited me to 2 significant figures. So I can actually take this a little bit further and incorporate grams. So if I want to know how many molecules are in 32 grams of fluoride, sorry, I'm going to first need to do a calculation to get my GFM. Just a little shortcut, I've already done that at this point, so we can just use that going forward. And now I'm going to start to plug in. So I say, okay, I'm starting with 32 grams. First thing that I need to do is I need to get rid of grams. So I need grams on the bottom. I'm going to put 112.8423 grams on the bottom, and that's equivalent to 1 mole. Now, if you're looking at this very step by step, that now gets rid of my grams. Now, the next thing I need to get rid of is moles. So I think about my possible conversion factors. I need moles on the bottom. So if I think about that 6.02 times 10 to the 23rd relationship, I'm going to need to have molecules on top. And it is important to either write out the word molecule or at least put that C on the end. If you're abbreviating it, that's an unofficial abbreviation, but I know it's kind of a lot to write. So 6.02 times 10 to the 23rd molecules is equivalent to 1 mole. Moles cancel. So now you're going to go ahead and you're going to multiply 32 times 6.02 times 10 to the 23rd using your little E, and you're going to divide that by 112.8423. And we're going to express this answer with 3 significant figures. 1.71 times 10 to the 23rd molecules. Now, if you're thinking about if this answer makes sense or not, this answer, we can kind of look at, we're seeing this exponent still of 23 here. So we didn't move our decimal place too many times, which kind of makes sense. We do have a smaller number over here. We did 32 times 6, but then we divided that by 110. So having that 23rd exponent kind of makes sense. How many grams are there in 4.9 times 10 to the 25th molecules of H2? So we're going to start by putting down our starting amount. So this time, the first thing we want to get rid of is molecules. So we're actually going to put molecules on the bottom. That's how many molecules we have in 1 mole. Now, in order to make this go into grams, we are now going to have to change moles into grams. So we need a gram per mole mass. Because this is H2, I took hydrogen's mass and multiplied it by 2. 1 mole of hydrogen gas has a mass of 2.01588 grams. This allows my moles to cancel. So you're going to go ahead and you're going to multiply across the top and then divide by that 6.0 times 10 to the 23rd. And this gives us 164 grams. If we kind of want to think about it, whether or not this makes sense, we have about 5 times 10 to the 25 molecules. That's a little bit more than a mole. If we look at, we have that factor of 10 there. Well, it's actually, not double that, but quite a lot more. So, it should make sense that we have a larger number here, which we do. 164 is quite a few moles of hydrogen gas. So a couple sample problems here to try. You can pause your video and I'll put the answers up with work in just a moment. I'm sorry about that. I realized I did repeat this problem because I had you taking it to atoms here. So since we did already solve this, here's the answer. What I wanted you to think about here is how many atoms this would be. So 1.71 times 10 to the 23rd molecules of FeF3. FeF3. And if we want to figure out how many atoms are in this, each unit of this would include 4 atoms. So we can say 1 molecule contains 4 atoms, and you're then multiplying that by 4. Oops. Ah. Sorry. To get 6.83 times 10 to the 23rd atoms. And here are your sample problems to try, so you can go ahead and pause your video and work on these. I'll plop the answers up in just a moment. So your first one is 6.23 times 10 to the 23rd molecules. So you started with your grams on the bottom to get rid of those, and then you had to have moles on the bottom in your next term to get rid of those. Atoms in this sample, you're multiplying that answer by 2, because LiCl would have 2 atoms. 1 Li, 1 Cl, and grams of silver nitrate. So you're starting with your molecules, you get those to cancel first, and then you change that into grams, and you get 133 grams there. Thank you very much.